Welcome to Sergio's Structural Engineering channel. For today's video, we are going to end the fundamentals of bending moment. And for that case, we are going to deduct which is the associated elastic bending moment for the steel shape already shown in the blackboard. Okay, in order to deduct the elastic bending moment for the section, we are going to study two concepts. The first concept is this one, is a stress-strain diagram for the steel grain material, okay? As you can see here, you have here the tension action and the compression action. This diagram is based on two important values. Yield point of the steel grain, that represent the plastic branch, okay? And the modulus of Young, okay? That represent the elastic behavior of the material. Another important point is the deformation here for this point limit that represents the range between elastic and plastic. It's just the yield point divided by the modulus of Young. Here, this behavior as a material is going to be applied in order to deduct all the normal stresses applied in the section, okay? So, to get the elastic bending moment, okay, we have to integrate all these stresses in the section to get the final value. So, we converted our 3D perspective in a lateral view, okay? We see here a portion of the steel section, okay? We are going to make a transversal cut against center of gravity, okay? And we have a representation of the normal stresses due to bending applied to the section, okay? In order to get the elastic bending moment, we are going to apply Navier equation. That is represented here in the blackboard, okay? Navier says that we can get the value for the stress, normal stress in each fiber of the section, okay, using or applying this equation. It is a certain moment, we will see that will be elastic bending moment, multiplied by a distance from the center of gravity to the fiber that we have to deduct the value of the stress, and then all divided by the second moment of inertia around axis Z. Okay, so let's operate the equation that we have here above, okay? Elastic bending moment is equal to the yield point for steel grade S355, okay? 355 megapascals, multiplied by the second moment of inertia, the value that we get in our second video, and all divided by the distance between the elastic neutral fiber to the top fiber of the section. Okay, so after make the operation, we get that the elastic bending moment for the section is 747 kilonewton meter. I think it's convenient after deducting the bending moment for the section, okay, to complete some values, for example, for the diagram of stresses, okay. So we know, of course, that the top fiber is under plastification, okay. So we get the value for the stress is equal to the yield point of the steel grade. But it could be also interesting to get the value for the fiber located at the bottom of the shape, okay. It is so easy to get the value to using the same equation that we have used previously for the elastic moment. But the only difference is we are going to use this distance, the distance between the fiber to the bottom fiber of the section. And then we are going to get the value of 224 megapascals. That you can see that the value is below the yield point of the steel grade. Let's advance a little bit. So we have made the diagram for the tensions. Let's go to the deformation for the fibers of the shape of the section, okay? Taking into account that we are working in the elastic range, so there is a linear relationship between the formation and steel stress for the shape, okay? So things that we can do is to get the deformation in the extreme fibers, in the top and in the bottom. In the top, okay, we are going to reach to the yield limit, okay, so it is so simple to divide the elastic yield point for the steel divided by the modulus of Young, okay, and this value of the bottom is the same procedure, but using, of course, the stress value that we have previously obtained in our calculations. It is very also interested reaching to the point that we have this deformation diagram to get the value for the elastic curvature that is associated with the elastic bending moment. It is so simple to get the value for the deformation to the yield point divided this point, okay, divided by the distance between the extreme fiber to the center of gravity of the section. getting the value of 6.13 10 minus 3, 1 divided by meter. We are getting to the end of the video for today. In the next edition, we will try to investigate which is the plastic ultimate bending moment for this section, when all the fibers get plastified, okay? Until this moment, I would like to say goodbye and see you in the next time.